Again, welcome to Unit 1, Part 3 lectures. Again, this is Unit 1, Part 3 lectures. In this unit, we are going to learn about numeric system. That's how data is represented in computer system, the numeric system. So our main objective is to understand the fundamentals of numerical data representation and also manipulation in digital computers. We know that again, in computer system, data are represented as binary numeric system, or we say the machine language, 0, 1s. Also here, we're going to learn the skill of converting between various Radix system. Radix basically means the numeric system. For example, we have a binary numeric system, which means the base is 2. The base value is the number of digits we have. So the binary number system, the base is 2, means we have only 0 and 1. Octa means 8. So the base is 8 because we have 8 digits from 0 to 7. Hexadecimal means 16, which means the base is 16 and the digits are from 0 to 9, which is 10, then from A to F, which is 6. So which is 6. So together is 15 digits. Which is 5. From 0 to 9 is 10. F is 5. So from A to F is 5, which is again 16 together. 16. Sorry, please. So hexa means 6. Decimal means 10. So hexadecimal, the base again is 16 because we have 10 digits and 6 alphabetical letters from A to F. So A means 10, F means 15. So that's why I'm getting a little bit confused. F is 15, but we have 16 together. That's 10 digits and 6 characters. So F means again 15. So those are the 3 most common numeric system we have in computer science. Most of the time, hexadecimal number system are used to give the address to the hardware device, the computer hardware devices, such as the memory, CPU, etc. So we normally use the hexadecimal numeric system for hardware devices, the computer hardware devices addresses. So let's start with the introduction. First, what is a bit? A bit is the most basic unit of information in computer, or I would say in computer system. So a bit stands for only one single 0 or 1. And 0 always means off. So in a digital circuit, when we say 1, we mean on. And when we say 0, it means off. So again, a bit is the most basic unit of information in a computer, and its state can be on, which stands for 1, or off, which stands for 0. Here also sometimes we may say high or low voltage. Again, high means 1, low voltage means 0. Also, most of the time we represent characters, symbols, everything in computer system, the data or the information as bytes. This is the reason why when we are going to buy any storage device, the unit, the capacity of the storage device unit is always in bytes. For example, I want to buy a flash drive. We have a flash drive of 1 gigabyte, 1 megabyte. Gigabyte means it's million bytes, which means that the flash drive can store up to million characters, symbols, etc. So a byte is a group of 8 bits. So we represent a bit as single 0 or 1, and a byte is a combination of 8 bits, represent 1 byte. So a byte is the most smallest possible addressable unit of computer storage. So one single character is always in a byte, one symbol always in a byte. Any data in computer system, the storage always is in byte. So here we say the term addressable. We use the term addressable here. means that a particular byte can be retrieved according to its location in a memory. Data in a computer system are always stored in a memory. And a memory is like a cell, a small boxes. Each cell have its own unique address. So a word is a contiguous group of bytes. Again, a word is a contiguous group of bytes. So words can be in any number of bits or bytes. The word size can be 16, 32, 64 bits are most common. And a group of 4 bits is called a nipple. That's another term. A group of 4 bits. So this means 2 nipples represent 1 byte. So a byte therefore consists of 2 nipples. A high order nipple and a low order nipple, 2 types. So byte store numbers using the position of each bit to represent a power of 2. So a binary system is also called the base 2 system. Why it's called base 2? Because a binary system have only 2 digits. Also, we have the decimal system. That's what we know. The base is 10. Why? Because the digits are 10 from 0 to 9. So our decimal system is base 10. It uses powers of 10 for each position in a number. We will go through an example of this soon. So any integer quantity can be represented exactly using its base, or sometimes we use the term radius. So radius means a base. Radius 10 means base 10, radius 2 means base 2, etc. So this is the example now. And the positional numeric system, we have a decimal number 947. We know 9 will be in the 100th position. 4 will be in the 10th position. 7 will be in a single unit. But as we saw earlier slide, decimal number system, always the base is 10. And the value of the exponent depends on the position of the digit. So since 9 is in position 100th, we say it's 10 to the power 2. 4 is in position 10th, it's 10 to the power 1. 7 is a single unit, so it's 10 to the power 0, which is, again, 1. So again, 9 times 10 to the power 2 plus 4 times 10 to the power 1 plus 7 times 10 to the power 0. If I do this calculation finish, I should get the same 947. The reason why we are explaining this concept is that a decimal numeric system, always the base is 10 because of the number of digits. Now we have 5836.47, which is a decimal number. Still, we are going to treat the whole part value same as we did previously. So we have to look at the position of 10 will be in a 1000th position. So, position of 5. So here we got 5 times 10 to the power 3 because 5 is in the position of 1000th. 10 to the power 3 is 1000. 8 is in the position of 100th, same as 9. So it will be 8 times 10 to the power 2. 3 is in a position of 10th, so it will be 3 times 10 to the power 1. And 6 is a single unit, so it will be 6 times 10 to the power 0. And that's what we have here, 5 times 10 to the power 3, because 5 is in the 1000th position. 8 times 10 to the power 2, because it's in the 100th position, 8. 3 times 10 to the power 1, because it's in the 10th position. And 6 times 10 to the power 0, because again, it's in the single unit position. So we do the whole number separate, and we do the decimal number separate. Decimal number, since we know it will carry the exponent to be negative value. So we saw that 4 is in the 10th position, second value. So it will be 10 to the power negative 1. And then 7 is a single unit, 10 to the power negative 2. Now, you can see that when we are going from left to right, we decrease the whole number, because a whole number, as we go from left to right, the value is decreasing. So the exponent will be decreasing from 2 to 1 to 0. But you can see that in decimal, when we are going from left to right, we're rather increasing it, because when we increase the decimal value, the value becomes lesser. If I have 10 raised to the power negative 1, it's bigger than 10 raised to the power negative 2. But if I have a 10 raised to the positive 1 and 10 raised to the positive 2, we know positive 2 exponent is bigger than positive 1. So that's why in decimal, we always start from left. We don't have no 0. There's no 10 raised to the power negative 0. We start always from 1. So 1, 2, etc. Now, if we do all this calculation finish, we can verify that our answer will be 5836. We can see here we have 1,000, 5,000, 800, and 30. So that will give us 5,836. Now, when you look here, we have the reason I don't mention 10 to the power 0 because it's 1. So 1 times any value is the same value, so it's 6. Now, when you look at the decimal, you can see here we have 1 decimal place. So it will be 0.1. 4 times 0.1 give me 0.4. 2 decimal places, so it will be 0.07. 7 times 0.01 will be 0.07. Now 0.4 plus 0.07 will give me 0.47. And this is another example for binary number system. So I have 11001 in the powers of 2 is, again, in the binary system, we start from left, then we increase the digits. So I'll start from this 1. So it will be 2 to the power 0, 2 to the power 1, 2, 3, 4. So I'm starting from right again. That's the difference. In decimal, we start from left, increasing the whole number. And in the whole number. When I say decimal, I don't mean a decimal point value. I mean the decimal numeric system. So let's go back here one time. You can see that in a decimal numeric system, 9, I start from the position 2, 1, and 0. Or you can say 0, 1, 2, the same. But when it comes to the float, the decimal point, we always start from left to right. The 1, negative 1, negative 2. So with decimal value, it's like a whole number. So I'll start from right, 0, 1, 2, 3, and 4. And the base is always 2 because binary. So 2 to the power 4 times 1, 2 to the power 3 times 1, because we have 1 here, plus 0 is 2 to the power 2, another 0, 2 to the power 1. The last value, 1, is a single unit, so it's 2 to the power 0. When we add these values together, we get 25. So this means 25 decimal number is the same as 11001 binary. Now, to check this answer, I can use the method whereby I will divide 25 by 2. The remainder will give me the binary number. So if I divide 25 by 2, the remainder will be 1, and the answer will be 12. So I get my first 1. Then when I divide 12 by 2, the answer will be 6, remainder 0. So I got the 0 here. And when I divide again by 2 again, it will give me 3, remainder 0. I get my third 0. But when I divide 3 by 2, I'll get 1, remainder 1. So I have the 1 here. Then when I reach the last value to be 1, I will add it. So I'll get 11001. So that is just to, again, check if the answer is correct. If I convert the binary number to decimal, if I convert the answer from decimal back to binary, it should give me the same answer. So again, very slow. I divide 25 by 2. The remainder is 1. Then that will be the first unit. So that will be the 1 here. The answer will be only, when you divide the value by 2, the remainder will be only either 0 or 1. That's it. So that will be our binary number. Next time I have 12. So when I divide 12 by 2, the remainder is 0. So I get my second 0 here. And then what I mean is this. So I get my second 0 here. I get my second 0 here. Now I divide by 2 again. This time I have 6. I will get 3, remainder 0. So I'll get my third 0. Then I will divide by 2. 3 divided by 2 give me 1, remainder 1. So I'll put my 1 here. When your answer is 1, you put the 1 to and join it. So our answer will be 11001. So converting between bases, we saw a few examples. Here we say we use the term radius system, that's again base system. So because binary numbers are the basis for all data representation in digital computer system, it is very important that you become proficient with this radius system. And also your knowledge of binary numbering system will enable you to understand the operation of all computer components, as well as the design of instruction set architecture. So in the earlier slide, again, we saw some few examples, but there are two methods for base conversion, radius conversion. We have the subtraction method and also division remainder method. The example I gave in the 25, converting it back to binary, I use the division remainder method. So you divide the value by the base, you keep the remainder until you reach the last value. If it's binary, the highest value is 1. If it's octal, the remainder should be between 1 to 7. You can't get 0 as a last value. The last value always will be between 1 to 7. Now, if it's a hexadecimal, it will be between 1 to F or Y somewhere. So now we saw the remainder division. This is the subtraction division. So here they say, suppose we want to convert the decimal number 190 to base 3. Remember, now we are using base 3. So you can see that the base will be 3. So we know that, first of all, I look at the value 190 as, okay, 3 to the power 5 will give me 243. No, I need to get the most highest value that will give me either 190 or less, but not more than 190. So that will be 3 to the power 4, which is 162. This is a subtraction difference. Now, if I'm doing division remainder, I will divide 190 by 3. The answer I get, the remainder always should be 012. The answer I get, I keep it, then I write the remainder there. Then I divide the answer again by 3, then keep the remainder until my last value should be between 1 and 2. It cannot be 0. It should be 1 and 2. If it's binary, it should be only 1 because it can't be 0. If it's octal, as I said earlier, it will be from 1 to 7. If it's a hexadecimal, then from 1 to F. So division, always I like the division remainder method because you just divide the value by the base, then you keep the remainder. You keep doing that till you reach the end, which shouldn't be a value that is greater than the base. It should be less than the base. So if base 2, it should be 1. If it's base 3, 1 and 2, base 4, 1, 2, 3, etc. But let's go through the subtraction here. So here we say 3 to the power 4 will give me 162. I can't use 3 to the power 5 because 3 to the power 5 will give me 243, which is 243, which is too big than 190. So I'll use the nearest one, which is 3 to the power 4. 3 to the power 4 give me 162. So I'll subtract. The method here, we are using subtraction method. I'll subtract 162 from 190, I get 28. Since I have 3 to the power 4, the next should be 3 to the power 3, 3 to the power 2, 3. Even if there's no value that goes in, we still have to write 0 because since I have 3 to the power 4, I have to get 3 to the power 3 because this will give me the number of digits. So you can see that in the next step, luckily, we saw that from 3 to the power 4, 3 to the power 3 is 27. 27 was good because it's less than 28. I subtract 28 minus 27, I get 1. But when I get 1, I should get 3 to the power 2. 3 to the power 2 give me 9. But 9 is too big than 1, so I'll keep 0. Anytime your answer is bigger than the value, I reach, because since we have 3 to the power 4, we have to get 3 to the power 3, 3 to the power 2. So even if there's no value, we represent that by 0. So that's why 9, we have only 1. So we represent it by 0, and that's the 0 here. Remember here we have 2, then 1, then 0. Then next, we do the same thing. We need 3 to the power 1. So 3 to the power 1 again is 3. 3 is too big, so we put 0. Then the last value, of course, will be 3 to the power 0, which is good. 3 to the power 0 is 1, so we keep 1. 1 minus 1 is 0. So our solution will be 21001. So if I convert 190 decimal number to base 3, my answer will be 21001. And hope this is okay. Let's go to another example. So another method of converting that this is the method for decimal. We'll see the example right now. Decimal to, again, base 3. We are using the same thing. Another method of converting integer from decimal to some other radius. But here we are using the same base 3 here. Again, the next example is the 190 decimal. The same example we did. And as I said earlier, this is the division one. We divide 190 by 3, we get 63. The remainder is 1. We divide 63 by 3. Luckily, it goes in 21. The remainder is 0. We divide by 3 again. 21 divided by 3 is 7. The remainder is 0. 3 divided by 7 is 2. The remainder is 1. And of course, 3 divided by 2 is 0. The remainder is 2. Don't pick the 0. As we said earlier, even if I put 0, 2, 1, still we know that 0 is nothing. So the answer will be 21001. So we can see that is the same as the previous example, which we have here, 21001. Here, subtraction, we go up, down, and we read the result up, down, 21001. 190, what is the base that will give me at least 190 or less? It was 3 to the power 4. What exponent is 28? That will give me at least 28 or less. It's 3. But now when I come here, the remainder is 1. And there's no way I can get 3 to the power 2 to be 1. So that's why we put 0. 3 to the power 2, 0 here. Here also the same thing, 0, because 1 and 3, 0. 9, 3, 3. Then the last value, 3 to the power 0 is 1, so bring the 1. So this is, again, the answer is the same. I always prefer the division method. The only thing, remember, when you divide down, you have to read up. When you divide up, and dividing going up, you read it towards down. So we also have the fractional values conversion also. And we can see an example here. For example, if I have 0.47 base 10, is the same as writing 4 times, as we said earlier, to the left. So 10 to the negative 1, 7 will be negative 2. So 4 times 10 to the power negative 1 plus 7 times 10 to the power negative 2. Now, if I have 0.11, this is a binary number, then it will be 1 times 2 to the power negative 1 plus 1 times 2 to the power negative 2. Again, remember, this is the 2 years stand for the 2 years. The 2 years stand for binary, and the 10 years stand for, again, decimal number system. So we see how we can get converting between bases. There's 2 methods. We can use division, we can use subtraction method, division remainder. And also, this is the example for the float or decimal point, not decimal number, that's decimal point. So for example, here we say we want to convert 0.8125 to binary. So I have 0.1825. It's not a whole number. If it's a whole number, we saw the example very straightforward. I will divide by the binary, divide by 2, keep the remainders, or use the subtraction method. But since this is again decimal, the first thing we do is that we have 0.8125. So we look for any value with the base 2 and the exponent value that will give us close to this value. And in this case, we have 2 to the power negative 1. So 2 to the power negative 1 will give me 0.5. The remainder will be 3125. Then I'll go to 2 to the power negative 2, which will give me, if I find the solution of this, it will give me 0.2500. Then I'll go to 2 to the power negative 3. And here we write 0 because, again, the value is 2. Couldn't get closer. So here I'm going to use a calculator. The reason why, if I divide 1 by 2 to the power 3 means 8. So divide 1 by 8. My answer is 0.125. You can see that 0.125 can't go here. It's too big. When the number is bigger, then you put 0 and then increment the exponent, since we start from 1, until we get the remainder 0 from here. So the next step, we can see that we get 2 to the power negative 4. That gives us exactly 0.0625. So the difference of these two will be 0. So this is where we stop. We don't stop at this 0. The reason why, because 2 to the power negative 3 was bigger than 0.0625. So we put a 0 digit. Then we move to the next step. 2 to the power negative 4 was 0.0. Okay, so since it's the same, the difference is 0, we stop there and we keep 1. So our solution is given to be, again, this is a decimal value, so it will be 0.1101. Also, we can use multiplication method. I'll multiply the value by 2 and I'll keep the whole number. And then the remainder I'll multiply by 2, I'll keep the whole number again. And then the remainder I'll multiply by 2, but when I multiply by 2, I get 0.5, so the whole number will be 0. Until you reach 1, and the last one 1. So you can see that we get the same answer, 1101, but it's point, so 0.1101. And I like this method because it's more straightforward to me. Or we can see when we use this method, again, we get the same answer. The only thing is that you have to start from negative 1. Always we start from negative 1. Then I know 1 by 2 is 0.5, subtract. Next will be negative 2 is 0.2500, subtract. Next is negative, to be 1 over 8, which is 0.125. It's bigger than 0.025, so you put 0 if the value is bigger. Then to the power 4 will be 0.025, so the difference is 0, so we stop here, 1. But here again, it's very straightforward. Just multiply, keep the whole numbers until you get 0, 1. So that's again the conversion between bases. There's another few method here. We can use what we call the, if the digits are so many, for example, we can see this example here, the digits are so many. The best way to solve this is to break it down. Now, if I'm converting it, for example, we have hexadecimal will be 4 bits, and then octal will be 3 bits. If I'm converting it to hexadecimal, I will take the first 4 digits. Again, we know the digits can be represented 0, 0, 0, 0 is 0, 0, 0, 1 is 1, 0, 1, 0 is 2, 0, 1, 1 is 3, 1, 1, 1 is 4, and we keep going. And if it's 4, then it's 0, 0, 0, 1, 0, 0, 0, 1, 0, 2, and you keep going to the end. So we will see an example here for a second. This binary bit is given to us, and they say we should convert it to hexadecimal. So what I did, hexadecimal is 4 bits, so we break it into 4. And I'll look for the value for 0011, which is 3, 0101 is 5, 0001 is 1, 1011 is 11, which is B. Then in octals, we said it to be 3, bits. So we divide it into 3 bits, and we get 32433. So those are another techniques we can use. So in conclusion here, we learned about the computer numeric system. Most important, how to convert from one base to another. In computer science or computer architecture, the most 3 common bases always is the octal, binary, and hexadecimal. But in actual sense, we always use the binary and hexadecimal. Hexadecimal mostly is for the computer component addresses, and then the binary, of course, more important. That is the computer language, the machine language itself. So again, wish everybody the best. And if you have any question, feel free to send an email. And thank you for your time.